Yeah. Ooh, excellent. Okay, well, many thanks to Yama Dixit, who's been helping co-host this week with us here in the Monsoon Seminar Series. So this week for Schedule B, we were joined here by Mara Limonta, who is from Milan, Bicocca. And so this week she will be presenting to us some published and new results from the Bengal Fan in terms of heavy mineral and sedimentology. And so again, just housekeeping as usual. It's been a while since I mentioned this. I think almost all of us are veterans here in the seminar series attending, but just remember to type in your question before you basically are called to ask questions. So pretty much without further ado, we'll hand it over to Mara and she can get on with the rest of her presentation for today.
Share my screen. Okay. Okay, maybe you see my screen. Yes. Perfect. So maybe we can start. So good morning and good evening, everybody. What I want to show you today is are some results on turbiditic sediment of Bengal and Nicobar Fan. The collection and discussion of this data is are possible thanks to other colleagues that you see here. And what I want to do first, I have to thank the organizer of this meeting to invite me and also to give me the opportunity to show you this data. And also I have to thank CNR IODP Italia, which has made possible the development of this project, high resolution provenance study of turbiditic sediment of Bengal and Nicobar deep sea fan, tectonic and climatic implication. In the last years, many studies on sedimentary basin, in addition to the mountain range, have provided new constraints on long-distance sediment dispersal in response to orogenic evolution. And we know that South Asia represents one key place to investigate the interaction between tectonic and climate. The uplift of the Tibetan Plateau and the Himalayan range control the distribution of Asian monsoon, and the Asian monsoon are associated to the most important erosion fluxes on the planet. So around 80% of the material eroded from the Himalayas is stored in the Bay of Bengal, which hosts a unique sedimentary record of the evolution of the Himalayan range. The aim of the project is to recognize the most significant erosional events from the Miocene to the present, to identify the contribution of different Himalayan tectonic domains and their variation with time, and to define, wherever possible, the interrelationship between tectonic activity and climate during the evolution of South Asian monsoon. And we pay attention also on the paleo drainage evolution. We analyze petrographic composition, heavy mineral composition, geochemistry and geochronology of turbiditic sediment of the Bengal and Nicobar Fan that you can see here in the map. Why we study turbiditic sediment? Because sediment can be considered as geological archives. They record the geological events that affect the source area, and this poor provenance signature is modified by physical and chemical processes during transport and during deposition. So we can analyze their provenance, but also we can analyze sedimentation processes. With our turbidity sediment, we want to analyze provenance. Then we want to compare compositional variability of turbiditic sediment with modern river sediment of Ganga, Brahmaputra, and Irrawaddy River and Bengal Shelf to highlight how physical and chemical processes can selectively remove less stable mineral and segregate different sediment fraction in different subenvironments. Finally, we want to detect and possibly quantify the relative dissolution rate of a less stable mineral during burial diagenesis, analyzing the compositional of different samples collected at different depth in the same core. To briefly introduce the area, you know that the Bengal and Nicobar Fan is the largest turbiditic fan in the world, and most of the sediment that we have here represent the erosional product generated in the Himalaya. We analyze sediment from collect during the IODP expedition 362 in Sumatra subduction zone. There are these two with the red point, and expedition 354 in the Bengal Fan. You see the 7 core they are collect during the expedition here. So let's start with turbiditic sediment of the Nicobar Fan. With the red star here, you can see the sample that we analyze in the first core and in the second core here. We analyze petrography, heavy mineral, and UPB detrital zircon edges. If you look at the bulk-petrography, you can see that from the top to the bottom, we can distinguish 4 different petrofacies. You see here a ternary graph with quartz, feldspar, and lithic. If you look at the petrofacies A that characterize sediments that are younger than 2.4 million years, there are these with the red point. We have feldspatolithoquartzose sand characterized by the presence of heavy mineral like micas and amphibole. If we go down, we have petrofacies B here with feldspathoquartzose sand. If you go down with older sample with an age of 8.2 million here, we have lithofeldspathoquartzose sand characterized by the presence of sedimentary lithics, and also in our deeper and older sample here of the 2 core that are older than 8.2 million here, we find also metasedimentary lithics. If we look at the heavy mineral, here you can see the heavy mineral concentration index that give us an idea of how many heavy mineral we have in our sediments. If you look at the composition, in the shallow sample here, the heavy mineral composition is characterized by amphibole, epidote, and garnet. While if you look at the deeper sample in the first core here and in the second core here, you have poor heavy mineral assemblages. You see the decrease of heavy mineral concentration index characterized by epidote, amphibole, and garnet. So the compositional variability of the turbiditic sediment can depend on different factors as provenance, hydraulic inserting, grain size, and diagenetic dissolution. So in order to extract the provenance signature, we decide that the provenance remain unchanged in the last 10 million years, and we look at the other factors starting from the diagenetic control. We know that during diagenesis, the pore fluid temperature increase and pore fluid chemistry can change, and the less stable mineral attack and dissolve. So if we assume that all our variability depends only on diagenetic control, we want to see a progressive decrease in heavy mineral concentration that we see in the last slides. And then if you look here, you have a ternary graph on amphibole, epidote, and garnet. Here you have the shallow sample, and if you go to the top to the bottom, you have a decrease of amphibole and increase of epidote, a decrease of epidote and increase of garnet. But if you look at our value of different sample, the garnet content should be double than actually observed in our deepest sample. So we want to find another factor that can explain the lack of garnet in the deeper sample. We look also at the grain size, and what we see here is that here you have the grain size with depth, and you can see the shallow sample are coarser, characterized by higher heavy mineral concentration index and higher percentage of garnet. Why? In the deeper sample that are older, they are finer, characterized by lower heavy mineral concentration index and lower percentage of garnet, but they have epidot. So in the shallow sample, we have a coarser sample with heavy mineral concentration index that is higher with garnet. In the deeper sample, we have finer sample characterized by the low heavy mineral concentration index and the presence of epidot. Sometimes the epidot garnet ratio can be useful to distinguish between Ganga and Brahmaputra sediment. We know that if this ratio is bigger than 1, we have a major supply from Brahmaputra, while is less than 1, we have major supply for the Ganga. If you look at the value in our sediments from the top to the bottom, we can see that, all our sample, the ratio is bigger than 1. So we have a major supply from the Brahmaputra, but this ratio decreases from the bottom to the top. And this would indicate that supply from the Ganga River has increased in relative importance through the time. But we are not sure, because this ratio can depend on provenance, but also we see in the last slide also can depend also on the grain size. If we look at petrographic modes that are less affected by intrastrata dissolution and hydraulic sorting than heavy mineral sweet, we can say that the observed vertical trend in composition can be considered as provenance related. So what we see here, we see that metamorphic detritus increases progressively absection. And in particular, we find in turbiditic deposit in the last 5.5 million years, sillimanite and sillimanite bearing metamorphic rock fragments. And this can indicate contribution from metamorphic rock of Greater Himalaya. You see here that volcanic detritus is very minor, so we can reject contribution from Sumatra magmatic arc. In order to understand better the provenance of our sediment, we analyze also UPB detrital zircon ages. These data are collected in the Geological lab of the University College of London. So what you can see here in the left panel, we have our data on UPB detrital zircon ages. We compare this with the Bengal Fan published in Blue Metal 2018, and we compare also them with representative modern river from Ganga and Brahmaputra. Here you have in the right panel the potential different source rock that are exposed in the drainage basin on the Brahmaputra and on the Ganga River. The most important part is this part on the Yalon sample drainage basin. Here the Yalon sample drain Lhasa terrain and also the Ganges arc. And then you can see here the 4 tectonic stratigraphic unit of the Himalaya, Tethys Himalaya, Greater Himalaya and Lesser Himalaya, and in yellow you have also the Neogene foreland sequence. Here you have also the rocks that are exposed in the Irrawaddy drainage basin in the Indo-Burma range, and you can pay attention also on the Summa basin, because in the next slide we compare this composition with our sediments. So what we can see here in a multi-dimensional scaling map, we compare the 2 different fan. The Nicobar fan here are indicated by the orange point. The Bengal are with the pink point here, and then you have the modern river Brahmaputra and the modern river sediment of Ganga. And what we can see here that the two fan plot separately with a little overlap here. And what you can see that the Nicobar fan sediment show a greater spread in the epsilon axis here, and this can indicate another input different to those of the Bengal fan. And also, if you look these sediment from the Bengal fan that are younger than 3.2 million years, show a closer affinity to the modern Brahmaputra river. And if you look at the age, we have an increase of age younger than 10 million years that is diagnostic of the eastern syntaxis. So you can look here in blue the Bengal and in the black the Nicobar fan, and you can see that we don't have this signal in the Nicobar fan. But if you look here, you have the Bengal fan in blue and the Nicobar fan in black here. You can see that the Nicobar fan show a consistent high proportion of age from 400 to 600 million years, and this could indicate a provenance from greater Himalayan sequence. In this, we compare also our fan with the Oligocene to Pleistocene sample of Surma Basin. They are the yellow point, and you can see that they plot within both fan. So in the article of Pickering, the sediment mass accumulation rate is also calculated in the two fan, and what we can see here that the temporal changes are not always synchronous in the two fan. The sediment mass accumulation rate is higher in the Bengal fan from 14 million years. We don't see this peak in the Nicobar fan, but the peak was reached from 9.5 to 8.3 million years in the two fan here. And then if you look here, you have the marked fall at 5.5 to 5.2 million years. After this, the sedimentation in the Bengal fan remained low, while we have three different peaks in the Nicobar fan at 3.4, 2.4, and 1.7 million years. Here you can see the reconstruction from 30 million years to the present. You can see the different accumulation rates in the Bengal and Nicobar fan, different sources and different pathways from the present to 30 million years. But if we want to understand the evolution of the Himalayan before this age, we want to study the rocks that are exposed in the Andaman and Nicobar Island. The Andaman and Nicobar Island are composed by the Oligocene Andaman Flysh. The Andaman Flysh cover the whole Great Nicobar and the western part of the Middle and South Andaman. And the origin of this Flysh is a subject of ongoing debate. Some authors propose that derive from the Ganga Brahmaputra, other from the Irrawaddy river. So we want to understand the provenance, analyzing then the petrographic, heavy minerals, and geochronology composition. So if you look here, we have our sample in a ternary graph. We have petrographic composition, lithics, and heavy mineral composition. All our rocks are characterized by lithofespato quartzose composition with metasedimentary lithic. In some cases, we have volcanic lithics, and heavy mineral assemblages is have a lower heavy mineral concentration index and are characterized by the presence of ultra-stable mineral, zircon, tourmaline, and rutile associated with apatite, chromospinel, and garnet. We compare also our rock with modern river sediment of Andaman and Nicobar Island, and also with Irrawaddy River, you see the yellow star here, and Bengal Fan, that is here, and Bengal Estuary in red and in blue. These two, Bengal Fan and Irrawaddy Fan or Irrawaddy River, can be the two different sources of our rock. So let's look at the difference between these two. If you look here, you have that in the Irrawaddy River, you have lithofespato quartzose sand with sedimentary lithics, and the heavy minerals are characterized by the presence of epidotes and amphibole. Why in the Bengal Fan here, you have lithofespato quartzose sand characterized by the presence of metasedimentary lithics and micas. Heavy minerals of the Bengal Fan, heavy mineral suite of the Bengal Fan are characterized by the presence of amphibole, garnet, that epidotes. So these are the two possible sources of our Andaman Flysh. We look also at the UPB detrital zirconages. Here we have our rock sediment, our rock sample here, and we compare these to Bengal Fan, Paleogene Bengal Fan. You see they are similar, and also to the modern Irrawaddy here. So what we want to do now is to develop a diagenetic model and apply this diagenetic model to the modern Bengal Fan and modern Irrawaddy to compare the Diagene's model and our sample. So we developed the model with another study that we do in the Bengal Fan in a core that go to depth of more than 3 kilometers. You see the changes in composition here. You see that heavy mineral concentration index decrease. And here you can see that from top to the bottom, we have amphibole that decrease, increase of epidote, decrease of epidote, increase of garnet from top to the bottom. So we apply our model in the Irrawaddy Fan from the modern here, and you can see this line, and also we apply this on the Bengal Fan here. And so here you can see our sediment. We can apply this model only on the heavy mineral because we don't have petrographic composition in the sample that we use as the starting part of the model. So what we can see here is that they are similar. So we can say that Andaman Flysh sandstone may be either Bengal derived or Irrawaddy derived. But if we put together here petrographic heavy mineral and UPB detrital zirconages, you have in the orange point our sediment, our rocks, Andaman Flysh rock here and here. And if we compare these with the Bengal Paleogene Bengal Fan, we see that they are similar. But this sample from the Corbin's Cove, and if you look, this is more similar to the modern Irrawaddy, but what we can see is the provenance from the Andaman Flysh is from a common continental crust source with minor contribution from a volcanic arc. So if we come back to this slide, how we can explain these different accumulation rates, sediment accumulation rate during from the present to 25 million years? They can explain by climate or tectonic. We analyze first the climate. What we can see here is that is a record of delta 18 oxygen that can give us an idea of the cooling and glaciation episode. And what we can see here that is important is that high resolution benthic isotope record and magnesium calcium derived temperature data show that this cooling at 7 to 5.5 million years was synchronous with the intensification of the South Asian winter monsoon. And we can explain this peak with this strong winter monsoon. So we have an increase of sediment accumulation rates in the two fan. But after this, it's difficult to show a closer correspondence to the increase in the monsoon intensity and the different path in the Nicobar and in the Bengal Fan. So we can explain this with a possible change in the path of the Paleo Brahmaputra River. So in the late Miocene, the Paleo Brahmaputra River flow directly south. So you have a huge quantity of sediment that go to the Bengal and Nicobar Fan. So we can explain this peak in the two fan. And from 5 to 2 million years, the drainage basin has been pushed westward by the expanding Indo-Burman wedge. And so you can see that we have a huge quantity of sediment that go in the Nicobar Fan, but less sediment go in the Bengal Fan. So we can explain this point with this. And if you look at from 2 million years, we have a huge quantity of sediment that go to the Bengal Fan, and we can explain this peak in the Bengal Fan. So to conclude, we can say that all this compositional, the compositional, mineralogical composition and geochronological composition suggest that the Nicobar Fan was a major sink for Himalayan-derived material. The downcore decrease in heavy minerals and the less stable mineral may be an effect of intrastratal dissolution, but also a grain side effect. So the progressive decrease in sedimentary detritus and corresponding increase of higher grade metamorphic detritus absection suggests an increasing supply for the Ganga River relative to the Brahmaputra. If we compare the Nicobar Fan sand and the Bengal Fan sand, they are not identical, they are similar. In particular, the Nicobar Fan sands lack young zircon from the eastern syntaxis that we find in the Bengal Fan sand deposit that are younger than 3 million years. And we can consider climate and tectonic to explain the evolution of the Nicobar and Bengal Fan. Now I can show you a little bit the idea of the work on the Bengal Fan. I received 2 weeks ago the new 18.4 new sample to analyze. We want to do petrographic and heavy mineral composition of silt and sands, also of turbiditic sediment. We request about 7 samples from the shallow core that are here in red, and about 15 to 20 in the deeper core that are in blue. So what we want to analyze is the intercore mineralogical variability to have information on the provenance change and diagenetic effect. And we want to analyze also intercore variability to check if we can see the lateral shift of dispersal pattern through the time. I will show you the first data and the analysis that we want to do in the first core. Here is 1454b. In the blue sample, we want to analyze petrographic composition in the fraction bigger than 63 and heavy mineral in fraction bigger than 15 microns. And then in other sample in red, we want to analyze 2 different fractions bigger than 63, and we analyze petrography, heavy minerals, and geochemistry. And we want to compare this with the fraction from 5 to 63 microns, where we analyze light minerals, heavy minerals, and geochemistry. Here we can analyze light minerals, and we cannot analyze petrographic composition, so we analyze only the light fraction. What we want to do is to analyze intra-sample variability to understand hydraulic processes and sediment mixing in the depositional environment. Here you see an example from the core that we ask for our sample. You see that is a sand, silty sand. And now I will show you the first data on this fraction. From the light mineral, we use an automated Raman collection around 1,500 points for each sample we analyze. And what we can do is to, thanks to Raman spectroscopy, is to identify different mineral, analyzing the diagnostic peaks of different heavy mineral species. And we compare our spectra with the spectra of reference. Here you can see what we use. And here you have some grain that we analyze. We can distinguish in the plagioclase between albite and calcium plagioclase. Here you have the peak typical of the quartz, and then we can distinguish of different feldspar, microcline, orthoclase, and sanidine. We use also an automatic mineral identification, and we compare the automatic with the manual mineral identification, and we can see the error is the 5%, so could be good. We can study the light minerals here, and we can distinguish between different minerals, and we can not study light the rock fragment here because we have this fraction. So these are our data. What we want to do after is to, when we have also the composition of the fraction that is bigger than 63, is to compare our data with the two source and the shelf and the delta, and also the magna estuary. If you look at the heavy minerals of this fraction, we analyze them with polarizing microscope and Raman spectroscopy. We analyze around 2,000 transparent heavy minerals for each sample. And if you look in the core, we have a very rich heavy mineral suite characterized by amphibole, epidote, and garnet that is diagnostic of orogenic Himalayan provenance. We want to do the same, compare these heavy minerals with Ganga, Brahmaputra, Meghna estuary, and Bengal shelf. I want to finish this presentation with this slide. Here you have the composition, petrographic and heavy mineral composition in the Bengal sediment system. So you have sediment from the Bengal, from the Brahmaputra river, from the Ganga river here, from the Meghna estuary, and also you have the shelf and the delta, the different heavy minerals and petrographic composition. And what I want to do in the next month is to understand where will the new Bengal turbiditic sediment plots in this graph, and also to understand their provenance. So thank you for your attention. So I can stop to share maybe. Okay.
Great. Thanks so much.
Okay.
Okay, so we'll allow people to queue some of their questions in the chat. Let's see. Okay. I did have a very minor question. It was mostly about the Ganga and how the Ganga prepared on someone, I think on the first MDS plot that you had shown. Again, I know that there's many samples, right? And I think it was maybe, I think it was detrital zircon It might have been from
Yeah.
the Pickering paper.
Yeah.
But it seemed like that all of the Bengal fan, and I think Nicobar fan samples plotted much farther away from the Ganga than from the Brahmaputra.
Yeah.
And that was the one where I think you might have clarified this and I could have missed it, but you mentioned that there was a potential other source as well. And I was wondering how well characterized the Ganga sample was, how representative, maybe. Yeah, that slide.
Okay.
Because the Ganga is just
So maybe
sitting out there. Yeah.
Yeah, is okay. Yeah, because maybe this part. Okay, I can put this here. Okay, perfect. So maybe this point that you see here derive most from the Ganga than from the Brahmaputra, maybe, because you have a greater Himalaya that you don't find in the Brahmaputra. So maybe when you use this plot, you look at the distance between the two samples, so it's something that is multidimensional, and so you put here, maybe it's also this. But if we look at the composition, also on the petrographic and heavy mineral composition, the Nicobar fan is more similar to the Brahmaputra and then the Ganga, but you have the apport of the apport of the Greater Himalaya sequence that is important, and this is also can come from the Ganga.
Yeah, to me that's just super impressive, because just how much the Ganga is essentially eroding out from the frontal Himalaya relative to the Brahmaputra. I mean, there's lots of other things that go along with it, but I just found that kind of a cool little thing that came out from that.
Yeah, also we for the composition, also we look also at the quantity of the carbonate to understand the Ganga and we can distinguish Brahmaputra and Ganga with the presence of carbonate, because in the Ganga you have more carbonate than in Brahmaputra. Maybe also we have to consider also this in our composition.
Yeah, that's a good point.
And also, if you look at the composition of petrographic composition, the Brahmaputra, you have more micas than the Ganga River. So maybe you have to use these data together. Yeah, maybe you have to use all the data together, and you can sometimes not everything are similar, but we have to compare everything, composition, petrographic, heavy minerals, and the detrital zircon ages composition. Okay, I can come back.
I think I see Sergio has his hand up, so.
Thank you very much, Mara, for your nice presentation. Just I would like to say that to add value to your big work, also the fact that you are investigating also the silt fraction is a key point in this ongoing study, because if you think about the past provenance studies, we have focused for a long time to the sand fraction. But you have demonstrated in this study that the silt fraction is fundamental to better understand the provenance through time. So I think that what you're doing, combining the classical method of microscope together with Raman spectroscopy, is really promising. So I would like if you can comment this new idea to work in the silt fraction for future provenance studies, and how we can use this possibility in the next future to improve our knowledge about source to sink processes. Thank you, Mara.
Thank you, Sergio. Yes, of course, the important part, because we see that the silt fraction is more important like sand in our sample. And in this day, I start to do the grain size of this core. And what you see is that we have a lot of material from 15 to 32 microns. So this fraction is important in our sediment. So what you see in the description is that you have a silty sand, but you have a lot of silt also in our sediments. So this is important to compare the different fraction. And with the Raman, we can analyze different grains, and we can also analyze what we cannot do in sand, because in sand we can analyze petrographic composition only in the fraction that is bigger than 63. So we lost this part that are smaller than 63. So with the Raman, we can analyze each grain, and we can say if they are quartz and other light minerals. And in this fraction, usually we don't find lithic fragment because they are bigger. So we don't lost this signature. So it's good. So we don't lost some data. We have only this kind of mineral. Maybe if in the future we use you know, Sergio, that you have the collection in our lab on the different light species, light mineral species. We can do a bigger Raman library, and so we can compare the new library with our grain, because now we are working on the Raman library that are published, and we say, okay, for example, in the presentation, you see that we use Freeman 2080 to distinguish from the different plagioclase and key feldspar. And but we say, okay, these spectra are okay. So we assume that are good, but sometimes we can have some composition that can change. So the best thing to do is to analyze with a scanning microscope and EDS the composition, and in the same point we can do the Raman, and so we are sure that this spectrum is this point have the same composition that we see in the Raman and the SEM EDS. So this could be also the future. We are working on this with Sergio and on different heavy mineral species and also in the light. And so this may be the future of the provenance study. I hope. Okay.
Great, thanks. We have another hand raised by Christian. So would you like to ask your question?
Christian. Hi, Christian. Oh, maybe you are too.
You're muted.
Okay.
Sorry. Thank you and buongiorno, Mara. Thank you very much for your presentation. That was really interesting, and I'm looking forward for the new results. Yeah. Just an observation I wanted to make on the figures where you are showing the accumulation rates, if you can.
Okay. Yeah. Maybe I can.
Because that is. Oh, okay. So this figure is misleading, actually, and it's important to take into account the full image of the Bengal fan there. Using only U1451 is wrong in this context. This is why we have drilled the transect of holes, yeah. And because the accumulation rates in the fan is subject to many different factors, and one of them is the deformation of the 90th ridge. Mm-hmm. The U1451 is located on the flank of the 90th ridge, which is undergoing deformation at that time. Yeah. And this is why you have a decline of accumulation at 5-6 million years. And then it is replaced by hemipelagic deposition. If you consider the hole and the U1455, which are more to the west in the fan, more axial. They show absolutely no decrease in accumulation rate. So it's wrong to propagate the idea that there is a decrease in accumulation rates in the Permiocene in the Bengal fan. It's a odd view of the problem and not taking into account the full information. So it's important. That's an error which has been done in this article, and unfortunately, it should be corrected.
Because we have to. They do this only on one core, so we want to. Now we have the sample, and also you present the data last week. And we have to do the same with the other core, and we want to understand also. We can, maybe the idea is to do and calculate a sediment mass accumulation rate with the composition, with the petrographic and heavy mineral composition when we have this. And because what we see in the sample is that sometimes we have samples that have the same age, but they are collected at different depths. So we have a different accumulation rate. So we can calculate this also using petrographic and heavy mineral composition. So we are working also on this. So maybe in the next month we have a new data on the Bengal, and we can correct also with the petrographic and mineral composition this graph.
Okay. Thank you. I have actually another small question. And I think that you and maybe Sergio might be able to answer this. So with the Raman spectroscopy and your kind of silty fractions, right? Usually when you're looking at the sand fraction, you can also get an idea of how diagenetically altered the actual grains are. So with the Raman spectrographic kind of method, I'm messing up the word here, but with Raman, can you identify how altered the phases are using their spectra?
No, because from the spectra you cannot, the spectra give you an idea of the diagnostic peaks, so give you an idea of the chemical composition of the grain. But with Raman, you can also do a grain size analysis of your sample. So and also you can look at the different corrosion feature. So you can also with Raman do like something like image analysis. And so you can also see the grain size and the corrosion feature in the silt. Maybe you can do this. So
if you want, I can add that you can see if you have a formation of autogenic minerals during diagenesis. So, for example, if you have titanium oxide like anatas or other cements, strange things, you can recognize properly these minerals. So this is important if you are doing a diagenetic study. But it's right what Mara is explaining about grains. Also, the use of a microscope combined with Raman is very important because you can see these corrosion features. And normally, what is nice is that Raman is confocal. It means that you can go on one grain and you can move inside the grain. So you can jump into the grain, avoiding the stain on the surface, and it allows us to recognize properly minerals also when they are weathered. And this is a big advantage respect the past, where you have a big box when you are not able to recognize things, so you put everything into these weathered grains. Sometimes you can recover a lot of information in this bin of weathered grains, and these are there. Just now with new technology, we are able to squeeze out information that are waiting just people like Mara to do this work.
Excellent. Thanks so much for clarifying that. That's really cool. I look forward to more of your results because that's 84 samples. That's a lot. That's a lot of cool information that's going to come out soon.
Maybe
Sorry,
okay.
I think I'll have to step in. I think there's some technical glitch with Tara's connection, and so yeah, I'll just step in and would see if there are any more questions here. No. Yeah, well, I think we would end this seminar here and thank Mara once again for this excellent seminar. And thank you all for attending. And then it is also being live streamed, as you all know, as Tara and Peter and Liviu have been organizing it. So yeah, it's available on YouTube for viewing later on. And yeah, well, thank you and have a good day, all of you, and good night wherever you are in the world. Yeah. All right.
Bye.
Thanks.
Bye.
Bye.
Thank you. Bye.
Thank you.
Bye.
Bye-bye. Thank you.